Okay, let's go. So today's still going to be a light day, actually. Nothing too serious. We're going to do a review of exponentials and logarithms. It's not meant to be comprehensive, not meant to be particularly good, just meant to jog your memory. If you've seen these before, it should be enough. If you haven't really seen them before and you are, or you're a little bit sketchy on them, I would recommend that you see the suggested problems in the text. This is mainly going over the very basic rules with very easy examples or sometimes no examples at all, just to make sure that we're all on the same page and we know how to look at certain symbols and realize what they are. So let's go over exponents first. So, AKA, sometimes you might call them powers, and you might see a notation here, something like x, and you have a guy that's up here to the top right corner. That guy is called the exponent of x. The big guy down at the bottom, that's called the base. And this expression it's called an exponential expression, but we'll talk about that a little bit more. And if a is a positive integer, that means whole number, then x to the a basically means you're multiplying x by itself a times. But we can, of course, extend this definition to non-integer values, which we will continue to do presently. So there are certain rules that these guys follow that I want to make sure you guys know. Number one, if I take two such expressions, they have the same base, and I multiply them, what's the new expression? Yeah?
X A plus B.
Right, you add the powers. And what if I take two such expressions and I divide them?
Subtract.
You subtract the powers. Okay. And of course, in the integer case, you can see that this will work because based on the definition, this means x is multiplying itself by itself a times. Now it's doing it by b times, so in total, it's a plus b times being multiplied, etc. And you can extend these guys as well and realize that you can cancel things out and you'll have this minus that number of cancellations. You can also take something that's to a power and you can raise it to another power, and that would give you what? What's that? Yeah, it's 8 times. What about x to the minus a? Yeah? 1 over x to the a. So I think you guys did a quiz today, right? In the other section. So the first problem 1 was me asking you a bunch of things with exponent. How was the quiz, by the way? How did it feel? It was okay? Well, the quiz today was a lot longer than a quiz would normally be, but I had a lot of stuff that I wanted to know if you guys knew. So.
Yeah, it was like too long for the time. Yeah. Just a little.
Okay, just a little. So how come with the first time I asked it, no one said anything? Like, oh yeah, it was okay. Like I said, your feedback is allowed. Don't be afraid. If you felt like the quiz was too long, say, I thought the quiz was too long. It's okay. We're all adults here. You don't have to, can't say anything to Mr. Smith. No, you can say whatever. I know it was a long quiz. Like, quizzes usually won't be that long. They definitely won't be double-sided. It's just that, had a lot of algebra to ask you about. Yeah, so we have that guy What about, say, x to the 1, x to the 0, which is the definition, it's just x. What is x to the 0?
1.
It's 1, provided that the base x is not 0, by the way. This you can see by setting a equals b in this expression. If you plug in a and b are the same, a minus b would be 0. And if a and b are the same, you're dividing something by itself. And so cancel out and give you 1, so you have that rule over here. And that's why x cannot be 0, because you would divide by 0, and we don't want that. That's the rule. Not really given any examples at this point, because it's more or less something that you would know already. If you look at, say, a 7th rule that I want you to be familiar with is, again, that exponential distribute across products. So if I take a multiplication and I raise that to a power, I can actually apply the power to each individual thing. This also holds for division. What about this one? If I put a fraction in the power, what does that mean? Yeah?
It would be the root of a to never mind. Yeah?
The root of a, that's what you mean? The a root?
No, never mind.
b root x to the power of a.
B root of x to the power of a.
I got it mixed up, sorry.
That's it. And it's equal to, you can take the root first and then raise that to the power. If your x is positive, well, not negative, you can do in whichever order you want. To make sure you don't forget, this is a little thing that, a little mnemonic I've known ever since I was a kid, and even today I haven't broken out of it. I still say it in my head. Laugh to myself when I say it. People think I'm crazy. One way you can remember this is flower power. So if you have x to the a over b, you kind of think of this like a flower. Right? The bottom is the root, which a root is another name for this guy. And so that would go with the b. And the top is the flower, which rhymes with power, hence flower power. So you know that the number on top is going to be the power of a, and the number on the bottom is the root that you're taking. So that would be it. And so, small example here, interchanging these might be useful because if you had something like, let's say 9 to the 3rd over 2, there are a couple ways you can think about that. You can think of this as 9 cubed and then take the square root. Or you can think of this as the square root of 9 and then take the cube. Now one way is easier to think about it than the other way, of course. And since the base 9 is positive, you can think of it in either way. This way is of course easier because that is just 3. And so 27 is what this is. As opposed to thinking of it this way, then you have to cube 9, what's 9 times 9 times 9, and then take the square root of that huge number. So a lot of times things will be interchangeable as long as the root behaves with this base. So you know that if the base is negative, you can't have an even root out here, etc. So those are exponents, some of the basic rules, and we actually did some of that stuff on the quiz today. Now one thing I want to talk about is exponential functions. Okay. So these are functions of the form okay. So if you have the base is just some number and the power is a variable, you have something that looks like that expression. This is a function, it's called an exponential function. Usually we'll think of the base as a positive number. But such a function is called an exponential function. Now, one thing you want to know about exponential functions is that they obey the rules of exponents, so all those rules, those 9 rules that I wrote down. You can combine 2 exponential functions in pretty much the same way. So these functions, algebraically, obey the above rules. This is a graph of an exponential function. Let's say y is equal to a to the x. For the time being, we're assuming a is greater than 1. If your a is negative, you can have issues if your power becomes even. So we usually don't worry about that. We have to deal with those very specially. Between 0 and 1, you can think of any such number as just 1 divided by a number that's bigger than 1. So ultimately, if we know how to deal with the base of bigger than 1, we know how to deal with everybody that we would care about. So for the time being, let's assume our base is bigger than 1. What would its graph look like? Does anyone know? What is the graph of an exponential function? Yeah?
A parabola.
It's not exactly a parabola, no. So a parabola is like this, like a U shape or a V shape. Yeah?
Is it half a parabola?
What does that mean?
Like just the to the right?
Well, it's a little bit more complicated than that. That's the expression that it looks like. I wouldn't say it's half a parabola, because this guy keeps going on forever. It gets smaller and smaller and smaller. It's always approaching the x-axis, but it will never actually hit the x-axis, right? Because hitting the x-axis means that y is 0, but if the base is bigger than 1, it's never going to be 0. And so it'll become smaller and smaller and smaller, but it'll never actually hit 0. You can say the x-axis is an asymptote here. So that's what the graph looked like. You can notice that it has certain properties that we'll care about. Notice that as your x gets larger, your y value will get larger. And as your x gets smaller, your y value will become close to 0. Right? Now, we'll have better notation for this later when we talk about limits. But an exponential function when the base is bigger than 1 is an increasing function that increases in this fashion, and it increases very fast. In fact, it will increase faster than any polynomial that you can come up with. So even if you compare this to a polynomial like x to the 1 million power, eventually this guy is going to be bigger than that. They will exceed any polynomial. This is a very important property of exponential functions. They grow very fast. Well, at least compared to polynomials. And notice here we can have the typical transformations. So let's say I had y equals minus a to the x. What would that graph look like? Yeah?
Flipped it across the x-axis.
Flipped it in the x-axis. So it would look like this. Okay. What if I had a to the minus x? What would that graph look like? Yeah?
Go the opposite way, like of a to x.
Well, what's the operation? When you make the entire function negative, no matter what the picture is, this is just an example, you would flip the entire picture upside down. When you make the input variable change the sign of the input variable, what does that do? Right, it flips in the y-axis. It flips this way. So that graph would look like this. Which, by the way, this kind of shows you what would happen if you had a number between 0 and 1. This is why I said once we know about this guy, we don't have to worry about the other case. So let's say I had y is equal to 1/3 to the x. I can really just think of this as 3 to the minus x, right? So once I figure out what's going on for numbers bigger than 1, numbers less than 1, they aren't a problem, right? Because I can write that as 1 over something bigger than 1. And of course, we can do both of these at the same time. So if you had, let's say y equals minus a to the minus x, Well, it's like you just take this guy and flip it upside down. That would look like that. Now, in these cases, even in the original, you should probably put this on. Notice that this guy would pass through 1. This will pass through -1. This will pass through -1. And the original one, the y-intercept, was also 1. This is because when x is 0, you get a to the 0, which we know is 1. So that's how the graph would look. So it is often very, very convenient when you're thinking about a function to think about the picture that goes along with that function. You can talk a lot about its behavior, and it will give you a lot of ideas about how to approach certain problems. If you can think about what this thing that I just wrote down would look like, how would it behave? And so it's very important that you know what the graph of an exponential function looks like. What else do we want to do? There's an important exponential function, one that we care about very much in calculus. Does anyone know what I'm going to say? Yeah, e to the x, super important function. It's not an understatement to say this is the most important function in calculus, and some mathematicians would say it's the most important function in general, in all of mathematics. It is extremely useful function. It's an extremely useful function. You can use it all over the place. This is called the natural exponential function. It's very natural to use this for calculus. Natural exponential function. We will refer to it affectionately as e to the x. It's a very important function. Now, e itself, this is a bona fide exponential function because the base is actually a constant. E is a constant. It's important that you know that. It's going to be very important for us to know when we're looking at something that's constant versus not constant for calculus. And so e is a constant. It is a number, kind of like how pi is a constant. So you know pi is a letter in the Greek alphabet. E is a letter in the English alphabet, but in mathematics, whenever it's in a mathematical expression, it actually means something. Its value is 2.71828, da da da. It is irrational, meaning cannot be written as a fraction. And it's a non-repeating infinite decimal. So no one has ever written down e in its entirety, no one ever will. It will go on forever, and the pattern, you have to figure it out as it goes. It is named for a guy called Euler. Should put that in quotes. Euler, he's a Swiss mathematician. One of the few mathematicians in history who was also very good and continued to be good in his old age. Mathematicians usually don't make any major contributions beyond their early 20s, but this guy, his entire life, even after he started going blind, he kept cranking out theorems, and he came up with this number, and so the E is for the E in his name, Euler. It's Euler's number, and basically where it comes from is it came from considering the following situation. Basically, he considered the idea, hopefully you guys are familiar with compound interest or something like that, but the idea is the following. If $1 is placed into an account, and compounded continuously. Compounding continuously is a phrase that means an infinite number of times. Right? So you're applying interest an infinite number of times. Like, it's not like every second or every day or every month. No, an infinite amount of times. And of course, it's a very theoretical kind of example, right? So if you place $1 into an account being compounded continuously, after 1 year, you will have, you might think you'd have an infinite amount of money in such an account, but you won't. You will have actually $E. That's where the number actually came from. He was considering, what if lenders really became loan sharks? How bad can it get? Right? I'm going to charge you 100% interest. Oh, I probably should say that. Compound continuously at 100% interest. Imagine that. Right? So in that ultimate scenario, you have 100% interest being compounded continuously. $1 will actually grow to be roughly $2.72 over the course of a year. And so that's where the number comes from. But it's a very important number. And so we can say here that E, based on the compound interest formula, we can think of it as this guy as x goes to infinity. Again, we'll have better notation for this later. But otherwise, it's a bona fide exponential function. Its graph looks like the graph that I drew earlier. Looks like this. After we discuss derivatives, we will talk about why this particular exponential function is a super important one and a super convenient one. And I'll actually use the exponential function to derive a lot of the formulas that we're going to be using in calculus. How many of you have seen this function before? So that's the exponential function. Now let's jump into logarithms, or logs for short. How many of you have seen logarithms? Okay, most people. Okay, so it should be a quick review. But they're also going to be a very important thing in this course. You need to be very aware of what they are. Here's the definition of what a logarithm is. Logarithm of a number to a given base. Is the power, or exponent, so logs are powers, they're just another name for a power. So the base must be raised to give the number. So the idea here is the logarithm to a given base. The base would be written down here of a number. So you can think of log as a function, and you're plugging in a number into it, and it will be according to some base. And this outputs the power that you have to take this base to get that number. So the notation here will look like this when you're writing it down, oftentimes. Log to the base a of b. Right? So you'd read that as log to the base a of b. That's how you read that expression. So what you should notice is that saying log to the base A of b equals c is another way of saying that if I take a raised to the power c, I will get the number b. So basically, if you have an expression like this, you can solve for the power, make it the subject of the formula by using a logarithm to the base here, right? It's an equivalent statement. It's just another way to think about an exponential expression. In fact, the logarithms have rules just like the exponentials. Exponents have them. And in fact, the first rule that I want you to memorize is in fact this definition. The fact that this equation means that is something that you should know. So let's talk about the laws of logarithms. First one is basically the definition. Log to the base a of b equals c means that a raised to the c equals b. So, example, we can say log to the base 2 of 8 is 3. Since if I take 2 raised to the 3, I get 8. Right? So that's what that expression is. This base raised to that power gives me that number, therefore I can say log to the base 2 of 8 is 3. Now, that kind of definition has all sorts of consequences that coincide with the laws of exponents, because it's just another way of looking at exponents. Here's the first rule. Let's say I have log to the base a of something raised to a power. You guys remember what that is? I can rewrite that. Yeah? Yeah.
N times log to the base a of x.
Right. 3. What if we have log to the base a of one expression multiplied by another expression? Yeah.
You can do log base a of x plus log base a of y.
Right. Turns into addition. And division? Subtraction. Right? Now, if you want to compare this to the original rules, you'll notice essentially what this is saying is if you take something to a power raised to another power, you multiply the powers. If you have two things of the same base and you multiply them, you would add the powers. If you have two things of the same base and you divide them, you will subtract the powers. It's really making the power the subject of the formula. And what you would notice is why you would invent something like this is it makes computations easier. Instead of having to raise stuff to powers, you now only have to multiply. Instead of having to multiply, you now only have to add. Instead of having to divide, you now only have to subtract. So they make a lot of computations where the numbers get really huge a lot easier because the mathematical operations, you can work with simpler ones. And so originally logs were invented for navigation purposes, nautical navigation, back when there was no GPS and we had to be calculating large distances and trying to make sure that people don't get lost at sea. So that's kind of where these guys came up. Someone just came up with an ingenious way of, here we can deal with really big numbers but simple calculations, because no one had a calculator at the time. They didn't exist. Another rule, it's important, it's going to be called the change of base formula. Sometimes you have a log in a certain base that's very inconvenient for you to use. So this rule provides you a way to actually change the base that you're working in. It says log to the base a of b is equal to log to the base c of b over log to the base c of a, where c is a conveniently chosen base. So remember I told you guys that the natural exponential function is super important. pretty much in any instance where we're working in a base that's not e, we can use this expression to convert to base e. C equals e is often very convenient for calculus purposes. But let's do a smaller example here. Suppose we had log to the base 4 of 8. What is that? Well, we know that this should be the power that when I raise 4 to, I get 8. What power is that, is the question, right? And you can start by guessing, okay, 4 to the 1 is 4, so that's not 8. Maybe it's 4 to the 2, well that's 16, so I overshot the target. So I know that number is somewhere between 1 and 2. Is it exactly halfway, 3/4 of the way? What number is that exactly? Expressing 8 in terms of base 4 is kind of inconvenient. So what we can do is choose a more convenient base. What would be a convenient base with these two numbers? 2, right? I know what 4 is as a power of 2. I also know what 8 is as a power of 2. So the base 4 is inconvenient for me. I can just use base 2, introduce base 2 by using that formula. And that will give me log to the base 2 of 8 divided by log to the base 2 of 4. Log to the base 2 of 8 is 3. Log to the base 2 of 4 is 2. So it's 3 over 2. It's exactly 1.5. Right? And you can check, because if you take 4 to the 3 over 2, flower power, this radical 4 cubed, that's 2 cubed, that's 8. That was actually the answer. So, any questions so far? So let's continue. So those are the rules that I would say you should know very well because they're not easily derived. But there are other rules that you can derive relatively easy. But I'd still recommend that you memorize, even though you can kind of figure them out. It's usually just easier, makes your life easier to just know them right off the bat. So let's do some of those rules. For example, what is the log of the number 1? So a is any base. What is log of 1? Yeah. Log of 1 is 0. Why? Because the exponential rules. A raised to the power of 0 gives me 1. So no matter what the base is, as long as it's a valid base, of course we're assuming the base here is greater than 0, and perhaps not equals 1, maybe even greater than 1. But log of 1 will always be 0. 7. What is log of 0?
1.
It's not 1. Why not 1? Well, if I apply the definition, you would say a raised to the power of 1 is 0. That's actually not true. It's not true in general anyway. That would only be true for the number 0 itself, but for logarithms you never are picking 0 as a base. If you have an exponential function, 0 is the base. It's just the function 0. There's no reason to do that. So this is actually undefined. If you have a positive number, there is no power that you can raise it to get 0, right? If I have 2, what power do you raise 2 to get 0? There is no such power. So log of 1 is 0, regardless of the base. Log of 0 is undefined, regardless of the base. Well, base 0 would work, but we never pick base 0. It's always a positive number. Here's another thing that you should know. think that is?
X.
It's just x. You can figure that out by applying a few of the previous rules. First, we can bring this power down according to rule 2. And without that power there, we just have log to the base a of a, and you might ask yourself, well, what is that? Well, what power do you have to raise a to in order to get a? Well, 1. So log to the base a of a is 1, and so you'd have 1 times x, you'll get x as the answer. So if you plug in an exponential function into a logarithm and they have the same base, the log and the exponential, they kill each other, you're only left with the power. Seems like something that's pretty convenient. It's also convenient that it works the other way around. So let's say I had an exponential function and in its power I put in a logarithm. Now that one's a little harder to derive, but it's not completely crazy to derive, but it turns out it's also x. Which means even the other way around, an exponential and a logarithm, they kind of cancel each other out. Quote unquote cancel each other out. Now, rules 8 and 9, at this point we can make a remark. Together they tell us that, let's say I'm considering an exponential function and a log function that has the same base. What can I say about these two functions based on 8 and 9? Let's phrase it another way. Suppose I call this function f of x and that function g of x. Okay? So this expression would be g of f of x, right? This expression would be f of g of x. So I have two functions such that g of f of x equals x and f of g of x equals x. So if I plug one into the other, I just get the original input back. What functions have that property? Yeah?
Inverse function.
Inverse functions. So the log and the exponentials are inverse functions. So if I consider them as functions, they are inverses of each other. So whenever I'm in an exponential situation and I don't want to be, I can use a log to get out of it. If I'm in a log situation and I don't want to be, I can use an exponential to get out of it. Knowing that is going to be important, especially for certain equations that we're going to want to solve. That idea is also going to help us get to the graph, but we'll cover that in a little bit. Let me just mention here rule 10, which is not really a rule, it's more of a notation kind of thing that I want you guys to be very aware of. So I mentioned that base e, the exponential, the natural exponential, is going to be a very convenient function for us to use. So you might wonder about, what if I put e as the base? It turns out that in Calculus 1, pretty much all the way up to all the classes before advanced calculus, we actually have a special notation for that logarithm. Do you know what that is? Yeah?
ln.
That's ln of x. When you see that expression, right, which is what I'm going to be using from now on, what it really means is log to the base e. So this function, whenever we see it, you should recognize it's a logarithmic function and the base is e. So it'll cancel out anything that has e as a base, etc. All those consequences fall. Okay. So in all the lower level math classes, that would be the case. Here. If you don't write a base, what does that mean the base actually is? It's 10. So if you just write log without a base, you can assume it's 10 in this class. If you write ln, you should assume the base is e. This guy here is the standard logarithm, which means its definition basically changes depending on what situation you are. In advanced mathematics, this would mean ln, because that's the standard. No one's going to work in any other base other than e once you're at a sufficiently high level in mathematics. 10 comes from the fact that this is used in science and engineering because we have 10 fingers and we count by them. If you're in computer science, this would represent base 2 because of binary. So the definition changes based on where you are, but for us, not writing a base means you should assume base 10. And writing this means you should assume base e. So you should realize that if I take ln of e to something, it is just x, e to the ln of something, well that's just x, etc. Right? They play together just like all the others would play together. So if I go back to all the previous rules and replace a with e, all the rules will hold, and you will have expressions like these working. Okay. Talk about the graphs. What would the graph of y equals log to the base a of x look like? Now, considering the fact that we know it's in the inverse of an exponential graph, what do you think it would look like? So here, let's say we have that guy. This is y equals a to the x. Right? Knowing that a log to the base a of x is the inverse of that guy, what do you think its picture will look like? How do you get the picture of an inverse function if you know the graph of the original function? Yeah?
You make it equal to x. Or you switch the places of y and x and you make it equal y.
That's if you want to solve for the formula. How do you get the picture? Yeah?
You can rotate it around the origin. And flip it across the x and y axis.
Yeah, a nicer way to say that is to reflect around the line y equals x, right? So you look at the line y equals x, and then you take the mirror image of that. And so if I would take the mirror image of that, I would end up with something that looks like this. And since this passes through 1, this is going to pass through 1 here. Another thing you will notice is that because this approaches the x-axis but never touches it, this will approach the y-axis but never touches it. So you can see here from the picture that log of 0 is undefined. There is no point on the graph where the input can be 0. So this guy will keep getting closer and closer to that, and this guy will keep getting bigger. It'll get bigger and bigger, but it's slower than an exponential. It'll grow much slower. In fact, it will usually grow slower than any polynomial to the same base. But we'll talk about that a little bit later when we get to limits. That would be what the graph of a logarithm looks like. So that's it. That's the graph of a logarithm. And of course, we can talk about its transformations. So there are some important properties here. Notice that here its domain is all x such that x is strictly greater than 0. It's going to be an important thing. The range, well, it's from negative infinity to infinity. It'll hit all y values. That's another thing that's important. And you can notice that as x approaches infinity, your y will also approach infinity. As your x approaches 0, your y will approach negative infinity. As your x approaches negative infinity, it does not even exist, so we won't even talk about that. We can also talk about negating the logarithm. Right? That means you just flip this guy upside down. It's going to look like that. You can talk about changing the sign of the inside. So we're taking that guy, flipping this sign. I can talk about you can do both at the same time. And you can end up with that guy, etc. We'll stop there for now. We'll do a little bit of computation with these two next time, and we'll actually start calculus. We'll start limits next class. That's where we are. Any questions? I know I was going kind of fast, but I was kind of a review. I expect most of you to be familiar with it. If not, I would suggest going to the suggested problems, work them out, because we're going to be using this later on. So it will be very good if you fully understand logs and exponentials. I will see you guys on Friday.